Okay, welcome back. So you were looking at how to draw a polytropic expansion process on a PV diagram. And again, I'm hopeful that that was pretty straightforward for you. Go ahead and label our axes here. So last time we looked at a polytropic process, and we said, well, it's got a little bit of curvature to it. And because this is an expansion process, we know that the initial state should have a volume that's smaller or lower than the final state. And so our polytropic expansion process would look like this. So again, good reminders for us right now is that work is process dependent. It's path dependent. So when we evaluate the work for that pressure volume process that's described in that figure, I'm kind of mixing units on you here. So these would be capital, which of course is a big no-no. So we'll go ahead and make sure we have it all correct. Like that. Okay, so on this diagram here, what we're doing is essentially evaluating the area under the curve. So hopefully you remember that from your math days, your calculus days, that if you integrate a curve from an initial state to a final state, you're determining the area under the curve. So that was one process. If we had a totally different process to somehow get from state 1 to state 2, this path, we'll call this path B, process path B, and this path, which is process path A, do not yield the same work. And that should be very obvious as you look at my sketch here, right? The area under the curve for path B is very different than the area under the curve for path A. Okay, so again, reminders. Work is process dependent. We need to evaluate it from the fundamental integral form every time. Okay, so enough about work. Now let's start putting the pieces together. What we're going to start with now is a discussion of the first law of thermodynamics. The first law relates changes in the state of energy of a system to the work and heat transfer terms. And what you see in the big bold print there is the example, the statement of the conservation of energy, or if you prefer, a statement of the first law of thermodynamics. It defines, the first law of thermodynamics defines that energy has to be conserved at all times. That means you can never create or destroy energy. All you can do is change its form. So from internal energy to heat transfer, from work transfer to a change in state, chemical energy to work transfer, all these little shifts are possible, but you can never create or destroy energy. You're probably already familiar with the conservation of mass that's usually introduced in a number of different subjects, including physics, that mass can never be created or destroyed. Same type of principle. Mass is conserved, energy is conserved. Okay, so in our big drawing at the bottom of that slide there, we can see that the change in the state from the energy at state 2 to the energy at state 1 has to be balanced by the heat transfer during the process from 1 to 2 and the work transfer during the process, occurs during the process from state 1 to 2. We already evaluated this, okay? We went through and talked about different types of work. We started having a conversation about the energy of the states. So we talked about how a system possesses energy. There's kinetic energy, there's potential energy, there's chemical energy. There are all these different forms of energy. So we're going to look at that a bit more closely. We'll also look at heat transfer, kind of briefly. We'll give you the really brief introduction to heat transfer. Okay. The details of the conservation of energy are everything. Okay, so we need a little bit of definitions here. So one is kind of a very unique type of definition, and that's a process which is adiabatic is uniquely defined as one where the heat transfer is equal to 0. Okay, so if I tell you your system undergoes adiabatic compression, you would automatically know, oh, heat transfer is equal to 0. Okay, and compression means you would know that the work transfer is expansion and compression work, and you would know that since it's a compression process, that that's going to be negative work. So all sorts of things are clicking into place now. Again, we defined kinetic and potential energy in the first unit. So again, that was probably a review for you. I hope it was a review for you, and that those weren't new terms. And now let's start talking about internal energy of the system. So again, uppercase means it's an extensive property in this case. So it's uppercase. That means it's an extensive property. It depends on the amount of material present. If we have a property that's been normalized by the mass, then we know that that's an intensive property. Okay. So we have the internal energy of the system on an absolute basis, on a per unit mass basis. As we go through and look at our systems, I'll tell you right now, you might intuitively think that the kinetic energy and potential energy of let's say, the air in a cylinder, or let's say water in a hydraulic dam that's being used to drive pistons, are the most important terms. In most energy transfer systems, now this is a generalization, so there are always exceptions, it's the internal energy that matters most, okay? That's the lion in the room. That's the gorilla in the room. Pick your animal analogy there. But the internal energy is the most important. And this is likely one of the first times that you've been introduced to this concept of internal energy. It is a property, a thermodynamic property of the system. So we need to be able to quantify the internal energy of the system. So that means we have to go back to our discussion of defining the states of the state of a system. And how do we do that? Okay, so that's where we're headed next after this little brief introduction to heat transfer. Okay, heat transfer is the energy transfer due to a temperature difference. So anytime you have a system that is at a temperature different than the surroundings, you're going to have heat transfer occur. So take, for example, as we sit in our chairs watching these videos, our body temperature is different than the air temperature around us. So there's heat transfer occurring, typically from us to the environment, if in this little example. But sometimes it may be the other way around. The air temperature may be higher than our body temperature, and the heat transfer will be into the system. Now, heat transfer is not a property. The heat transfer is more analogous to work transfer. Heat transfer, like work transfer, depends on the process path. And like work transfer, which has a sign convention associated with it, so does heat transfer. Heat transfer is positive if it is into the system, and it is negative if it is out of the system. And the sign convention for work transfer and heat transfer are from the origins of power generation centuries ago. So essentially, we generate power by burning things typically. So we have combustion systems that we use to heat something, and that heat is then translated into work. So heat goes in, and we considered that a positive thing, and work goes out of the system, and we considered that a beneficial thing, both positive and beneficial. So our sign convention is associated with the tradition of power generation in the world. So again, heat transfer is negative. If it's out of the system, it's positive. If it's into the system, and if you're ever having trouble remembering that, just remember, how do we generate power? Power is out. That's a positive thing, a good thing. So work transfer out is positive. And we do that by typically adding heat to a system. So heat transfer into a system is positive. So again, the sign convention for heat transfer is typically opposite that of work, and it's because of the tradition associated with power generation. Okay, to further compare with work transfer, we know that we had some nice integral expressions, and we know that since this is a process-dependent variable, that typically we would need to do an integral to evaluate the heat transfer. The catch is those expressions are pretty tricky, and we are not going to consider those in great detail in this class. We're going to make some pretty bold and big approximations for how we handle heat transfer, because that's an entire discipline in and of itself, is how to evaluate heat transfer. Okay, so what I want you to do is to think about the expression that you see on the screen now. What's wrong with this statement? What we're saying is that the integral of the differential amount of heat transfer is equal to Q2 minus Q1. And I'll tell you there's something wrong with that statement. And what I want you to do is come back with an explanation of what's wrong and how do you fix it. Thank you.